Hallo, guten Tag. Johann Jomuktikel is my name. Normally, I actually do those videos in German, but I realized like in our university, we sometimes have a master. Some people that don't really like speak German. They came here from other countries and do speak English, and English is actually more spoken than German in the world. So I told myself, why not make a video in English that could help like a lot of people. What I'm talking about here are basically stuff that were done in the bachelor degree, but okay, when we get to the master, the bachelor degree might be like so far away behind us that we forgot a lot of stuff. So what I'm gonna be talking about today is the force method. So how do we calculate forces or internal forces or reaction forces on a system that's statically indeterminate? And yeah, so let me write that down already. Statically indeterminate system. The force method. I got a similar video in German already, but since I didn't want to do exactly the same exercises, I'm gonna do like new exercises here. So for people that normally do speak German, just a possibility for them to see a little bit something new and just like revise the stuff they, let's say, know already, or don't, whatever. And it's also the possibility for them to get the words in English, so the German, the English words. So first method, just for German speaking people to know what we're talking about here, das ist das Kraftgrößenverfahren. So throughout this, sometimes I will just write the German words so that German speaking people don't get lost or confused. So what are we talking about here? We basically got a system that's statically indeterminate. First, we need to be able to know that the system is statically indeterminate. This is the system I'm going to take here. Pretty simple system. The load we have there is a distributed load. Let's call it small q. So how do we know that the system is statically indeterminate? First, we need to check it. We got some formulas. I'm going to write a very simple one here. Let's see. I maybe need to change the letters I'm using here because those are with German words, but we will manage. A plus G minus 3 times N is like, let's say, let's call it G, like the degree of statically indeterminacy. Let's call it like that. Where A here stands for actually support reaction. So the German was Auflage and it's for support reactions. G here stands for the German word Gelenk, and it stands here for, let's say, range reactions or range forces. And here is basically the number of bodies, okay? Anzahl der Körper, number of bodies. And when I'm talking about bodies here, I'm really talking about full element. Like it doesn't matter if it's a frame, if it's like an arc, we consider it as an element because there's another formula where when you got a frame, you're gonna consider tile bars, partial bars or partial rods. I'm gonna show that formula there. Basically, this is the easiest formula someone can use, and beware that this formula will not give you the right results if you got a closed system. What do I mean with closed system? It's something similar to this. Those corners here are transferring all the internal forces, normal forces, shear forces, and bending moments. So there's like no range here. The system are called closed because if we draw them like in a better way, it's gonna look like this. And with my pencil or with the pen right now, if I go around this inner part here, I mean, there's like no way that I can go around all the borders or all the boundary of this system without lifting up the pen and coming back here to go around that system. that's what we call like a closed system. I mean, I could stay here. If I don't want to lift my pen, I'm just going to stay in here. I will never go out. I never go around all the system because it's closed. An open system will be a system very similar to this one, but that's open, would be something like this. And you can see that here, without lifting the pen, I can go around the whole system. This is an open system. Okay. And here for system as like this one or combination of element that looks like this formula is going to work. So there's no need to use the more complicated formula that I'm going to give later. I'm going to state later. Furthermore, why do I say this exactly? Let's look at this small example. Let's take this closed element and try to use that formula. What do we have? We basically have one body. So n is equal to 1. The number of reaction forces is 3. That's a clamp support. So we got 3 forces here and 3 forces there. That's like 6. So A, it's 6. G, Gelenkreaktion or range forces. We got no range here because we only have one body. You can only have ranges if you have 2 bodies that are connected with each other. So there's no range here, and with that, no range reactions. And what about n? N is 1, like I said already. So we put it in the formula and we get something like 6 for A plus 0 minus 3 times 1 is 6 minus 3 is 3. Meaning that the number of reactions or the number of unknowns, let's call them like that, number of unknowns, those are basically the forces that we want to calculate. So reaction forces or range forces, those are the number of unknowns. And here 3 times n, those are actually the number of equations that we can write. Like we can write 3 equations per body in the plane. So number of equations available. And in a basic math problem, to be able to solve a system of equation, you need to have as much equation as unknowns. So if you have like more unknowns than equations, you cannot solve it. If you have less equation than no, that's the same. And if you have more equation than unknowns, actually it's not really possible. Some equations are being repeated there, and yeah. But in our case, if we actually have more equation that we can write than unknowns, that means the system is like kinematic. Like there's no discussion about it. It's definitely kinematic. But if we have the same number of equation as of unknowns, we still need to check, that's actually the mathematic way, we still need to check that all those equations are linearly independent. And the way we do that in our static problem is just by checking that the given system is not kinematic. Yeah, and if we have more unknowns than available equation, it means the system is statically indeterminate. So we have more unknowns than equation available. We need to find those unknowns with extra equation because there's no magic in here. Like mathematically, if you have like 4 unknowns, you need 4 equations. If you have 4 unknowns, like in this problem here, this vertical force, let's call it A, V for vertical. The horizontal support reaction here, H for horizontal. The support moment, M for moment. And let's call this point B, V for vertical. So we have the 4 unknowns, only one body. Let's try that formula right now. What do we have here for an element? It's just a beam. So it's A, number of support reactions 4, plus G, the number of range reaction 0. We only have one element, so no range between 2 elements or something like that. minus 3 times the number of body, only one body equal to 1. So this system is statically indeterminate to the degree of 1. Yeah, that's actually what we can say there. Now, going forward here, I want to show why this formula is not going to work for a closed system. So when we use that formula here, we find that it's 3, right? So this system is actually indeterminate to the degree of 3. Basically, we have 3 unknowns that are too much. That's what our formula wants to tell us. So our formula here wants to tell us that such a system, if we just keep the support clamped and we draw it like this, our formula wants to tell us that this system here is statically determinate. So if we use our formula on this one, we should have n equal to 0. This is actually not true. I mean, we can say that the whole thing here is a body, is one body, and we have only one support and 0 hinge, and we will say that n is equal to 0. Seems correct this far, but what happens with a system like this one, where I just cut that middle beam? By cutting this middle beam, what does that mean? It basically means that inside here we have the normal forces, the shear forces, and the moment, and I remove all of them. So I remove 3 unknowns from this system to this one. 3 unknowns, 3 internal forces were removed. And I get this system, okay? And if I check the degree of statically indeterminacy on this system, I'm gonna have like, okay, only one body, because you can see that I can actually go around the whole thing. It's an open system like we said we need it to be able to use that formula, that simple formula. It's an open system, okay, it's just one body, and we got 3 reactions here. Okay, so here n is equal to 0. Okay, so this is a statically determinate system. If this system is statically determinate after I've removed 3 internal forces, it means that the system over here was not statically determinate. It was n equals to 3. And it means also that the system before that, when we still had 2 clamp supports, could not be n equal to 3, but was n equal to 6. So this formula didn't work on this system. Of course, if someone knows exactly like that it doesn't work because it's a closed system, and that he needs to take into consideration those extra internal forces that needs to be taken away for the system to be open, blah blah blah, he can use the simple formula. He finds 3 and he knows, okay, we still need to remove, we have 3 internal extra forces there that needs to be removed too. So it's 3 plus 3 and he got 6. He can still use the first formula if he knows what's actually happening. But if we don't know that, and if we're not sure, the formula we use is this one. It looks like this. I'm gonna call it G again, like the degree of statically indeterminacy. I just made this up, so I need to write it extra. Degree of statically indeterminacy. I'm going through a lot of stuff here that I've actually already done in German videos, but this is like the first English one, so I need to go through all of them again to make sure that you get it. But actually I got videos on it. So here for the statically indeterminacy, I got the video named Baustatik Grundlagen statische Bestimmtheit. Baustatik Grundlagen statische Bestimmtheit. And in that video, I actually go really deep in that topic, how to get the degree of statically determinacy or indeterminacy. So now further here with the other formula, it looks like this. A plus 3 from B minus K minus A, where A is like again Auflage or support reaction. So support reaction. P stands for Teilstäbe partial, let's say partial bars oder Teilstäbe. Ja, ich habe es ein bisschen andersrum gemacht diesmal. Teilstäbe. K stands for Knoten in German or node. And S stands for restraint. In German, it's called Nebenbedingungen. So this formula is a little bit more complex, unnecessarily complex, I would say, but take into consideration all those traps from closed system, if we should call them traps. First thing first, let's try it on that same system and see if we get the right solution. Like we said, this system here, for it, we should get G equal to 6. It's not only those 3 reaction forces here that are too much, we also have 3 internal forces in there that are too much. Okay, so it should be 6. That's the result of everything that I said here. Maybe it was confusing, but actually that's what we should have got. I call this N because now that's how it's called, but let's call it G, the degree of statistical determinacy. So here's the actual solution. So this is 3 here, this is 0, and the G that we first found here, this 3 is not correct, cannot be correct. And the proof was all everything that we did there. Okay. Blah, 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 blah. So let's use that formula. The number of support reactions, 6. We know that already. 6 plus 3 times partial bars. What do we call partial bars? The whole thing here can actually be considered as a frame. And with the first formula, we will actually consider the whole thing here as one body. And if someone is aware that this system is closed, he will say, okay, it's one body and I still need to remove 3 internal forces. But now when we speak from partial beams, those beams are always straight lines. I'm a little bit hesitant on the word straight here, but they're always, let's keep it straight. Straight lines between nodes, and nodes are basically, okay, you know what nodes are. They're just those points here. Every time like there's like a change in the geometry or something, change in the direction of the beam. So we have nodes here. Here's one node, that's another node. So this is one partial beam or partial bar. Here's one node, there's another one. This is a second partial bar. So let's count those partial bars or partial beams. Here's 1, P1, P2, P3, P4, P5, P6. So we got 6 bars, 6 partial bars. 6 of them, okay, minus the number of nodes. Let's count the node K1, K2, K3. Okay, the nodes are those. K2, K3, K4, K5, K6. 6 of them. 2. Okay. Minus the number of restrictions. Here we have no restriction. Okay. But I still need to tell you what restrictions are. So I'm going to take another example. Let's calculate this first and then I'm going to explain exactly what the, okay, not restriction, restraints. I'm going to explain exactly what those are. So here we have 6 plus 3 times 0, so 6. The formula works, nice. So what are restraints? Let me take another example to explain that. Let's say I have a hinge, like an actual hinge. When I go from this element to the next one, to the second one, or from this body to the second body, because of the hinge, one internal force needs to disappear. In this case, is the moment. So that internal force that's disappearing is counted as one restraint. Wird als eine Nebenbedingung aufgezählt. So how many internal forces disappear when I move from this body, from body 1 to body 2, for example? And if I have another body in there, let's say I have something like this, then we have more restriction there, or more restraints, sorry. So first, the moment needs to disappear when I go from body 1 to body 2. It also needs to disappear when I go from either body 1 or 2 to body 3. So how many restraints do you actually have when on the same hinge you got many bodies that are like joined to that? The thing is just like the number of bodies connected to through that hinge minus 1. So number of restraints here, number of restraints is equal number of body connected together through that hinge minus 1. So here 3 bodies minus 1, 2. We actually got 2 restraints there. Okay, so here 3 minus 1 equal 2 restraints. Okay, and the way I counted the number of restraints here is the same way we're gonna use to determine in the first formula. If we want to use the first formula here, it's the same way we're gonna determine the number of hinges that we got here. So here we don't only have one hinge, we got 2 hinges. 2 hinges, and one hinge got 2 hinge reactions or hinge forces, a vertical one and a horizontal one, or a one in the length direction of the body of that element, and the other one perpendicular to that direction, or normal to that direction, take it as you want. Yeah, so there's only one node here, nur ein Knoten. But there's like 2 hinges here, 2 Gelenke. And we got 2 restraints here, 2 Nebenbedingungen. Also aufpassen. Be careful about stuff like this. Let's use the 2 formulas for this system. Let's use the first one. The elements we have here are not closed, so this frame is like an open element, that 1, 2, and that rod, obviously. So number of reaction forces, we got 3 here and 3 there. I don't know what I have clamp supports today. I draw them so much. I like them so much, it seems. So 3, 3, 2, that's 8 for A, plus the number of hinge reactions. We have 2 hinges, like I said, 3 bodies connected together through the same hinge. So hinge. That's actually 3 minus 1 equals 2 hinges that we have there, and every hinge got 2 reaction forces. When we cut through a hinge between 2 bodies, let's say we have a hinge here between 2 bodies, we cut through that hinge, we got something like this, those reactions. Let's call this HV and H, the first H for hinge, the second H for horizontal, and here the V for vertical, and on the other side just the same forces, just in the other directions. So that's why we got the number of hinges times 2, because each hinge got 2 reaction forces. So it's 2 hinges times 2, and then minus 3 times the number of bodies, 3 bodies. So What we have here is 8 plus 4, 12 minus 9, 3 is the number of, is the degree of statistical indeterminacy. And there's actually other methods I talk about in ja, ein anderes Video, glaube ich. Es wird scharfes Hinsehen genannt und nee, eigentlich dasselbe Video. Und in diesem Video dann gebe ich dann Methoden, wie man vom Ansehen, also allein vom Anschauen die statische Bestimmtheit bzw. Unbestimmtheit erkennen kannst. Also man benutzt dann Sachen wie Aufbauregel und so. Man bildet das System auf aus bekannten statisch bestimmten Systemen. Beziehungsweise man baut ein System ab, bis man zu einem statisch bestimmten System kommt, zu einem bekannten statisch bestimmten System kommt. Und man muss einfach wissen, wie viele Kräfte habe ich da abgebaut, bis ich letztendlich zum statisch bestimmten System gekommen bin. Und das wäre der Grad der statischen Bestimmtheit. Und ja. So there are actually other methods that I also show in this video, a little bit more, let's say, advanced, where you can just look at the system and know the degree of such indeterminacy. We use some methods like, okay, I don't know how they call it in English, but basically we're looking at the system and we're like checking how many internal forces or support reactions need to be removed from that system until we reach a system that's known as statically determinate. And the number of reactions or support reactions or internal forces that we had to remove up to that point is exactly the degree of such indeterminacy. Yeah, so we can do it by removing reactions, or we can just like take a statically determinate system that we know already, and we add elements, we add reactions or bars up to the moment when we reach the system that we actually have in front of us in the exercise or in the exam or whatever, and the number of reactions we needed to add or the number of bars we need to add is the degree of statically indeterminacy, because the starting point was a statically determinate system. Yeah, further informations in that video over there. Let's move forward. Now the second formula still need to be used. Wow, 30 minutes, and those are just the requirement for the first method. Whoa, I hope it's not gonna be too long, this video. The second formula, so G is equal to support reactions 1, 2, 3, 4, 5, 6, 7, 8. That's known, plus 3 times in the brackets partial bars or partial beams. We have 1 here from this node to that one. 1, 2, 3, 4, 5. 5 partial beams minus the number of nodes, 1, 2, 3, 4, 5, 6, minus the number of restraint. How many restraint do we have here at this node? We got like 3 bodies there in contact for the same node. The number of restraint is number of bodies minus 1, so 3 minus 1, 2 restraints there, minus 2 equal to, so here we have 8, here we have plus 3 times minus 1, so 8 minus 3, 5 minus 2, the answer is 3, and it matches. So I guess after this, and after maybe some repetitions going through those examples again, everyone should be able to determine the degree of statically indeterminacy. So for the example we want to calculate here, it's pretty easy. The degree of statically indeterminacy is 1. That we did already. That was statically determining the degree of statically indeterminacy, or the degree of statically determinacy, whatever. So in our case, it's x1. Moving forward and getting actually in the first method, the topic of this video. But what we did before was necessary. If it wasn't known, it was necessary. If it was known, it was still necessary as a revision. So, what do we have here? We have a system that's statically indeterminate, meaning, I repeat it again, we got more reaction forces than equations that we can write. Let's actually check if that's true. Maybe I'm lying here. Let's check if we really don't have enough equations to solve this. AV, MA, AH are the forces we're looking for. The load is known, it's a distributed load named small q. We don't need the value, come on, we're going up, don't need it. The length is L. And here we have a BV. Let's start writing our equation. Some of the forces in the horizontal direction, I will just write it like this. I know some people want to have it like this, sigma Fx external applied on the body that needs to be defined, body 1, whatever, should be equal to 0, and then column, and then write the forces if you want to do it like that, but I will just do it like this further on. AH plus nothing, no other horizontal forces, should be 0, so AH is 0. Wow, we know a force already. Very good. By the way, it's the fact that the system is actually indeterminate doesn't mean we cannot compute any force or we cannot calculate anything without the force method or the displacement method. That's another method I'm going to talk about later. We can do that. We can calculate some, but we cannot calculate all of them without going through one of those methods. There's also something we call superposition principle. Actually, I will talk about that in my crash course for engineering mechanics 2, so you can also check on that one. Yeah, so some of the force in the vertical direction. What we're doing here is we're checking if I was actually saying the truth or if I was lying. We're checking if we don't have enough equations to calculate all of this. Some of the forces in vertical direction, AV plus BV minus the resultant of our distributed load, that's Q times L minus QL is equal to 0. That was the first equation was this one. We actually found AH with that. That's good. Only 3 unknowns left. AV plus BV minus QL equals 0. That's one equation with 2 unknowns. We cannot do anything further with that. Let's go on with the sum of the moments around node A should be equal to 0. I chose this one as the positive direction. I'm free to do whatever I want when it comes to that. So minus MA, AH and AV are going to disappear. Both of them don't have any lever arm, so they have a moment of 0. Then BV with the lever arm L turning in my positive direction, and then my distributed load is not to be forgotten. Q times L will be the resultant times L half will be the resultant is applied here in the middle. I'm assuming by the way in this video that engineering mechanics 1 is known, so that every one of you know exactly how to compute support reactions and stuff like that, and how to get internal forces quite quickly. I'm still gonna calculate them, but I don't expect you to be unaware of how it's done. Minus MA plus BV times L. Where was I? QL is the resultant. R, what I call that, is applied in the middle, so the lever arm is a half L. So QL square half, and it's turning in the negative direction for me, equals 0. So what do we have there? The first equation was used already, we don't need it anymore. The second equation and the third are the only one that's remaining, and we got in those two equations 3 unknowns named AV, BV, and MA. That's not mathematically possible. The only thing we can do here mathematically is like write all of those unknowns in function of one of them. So write maybe everything in function of AV, function of BV in function of AV, MA in function of AV. But if we actually want to have exact values for all of those unknowns, we need a further equation. Okay, So, what's actually the logic behind this? Before I get deep in the first method, the logic behind this is the following. We say, okay, we have too many unknowns. We cannot compute this. We need a further equation. Okay, we had four unknowns. We need four equations. We can only have three equations from the three balance equations. Let's say sum of the forces equals 0 in both directions, x and y, and then sum of the moment. And we need a fourth equation here. That equation is going to come from displacement, from what we call compatibility. So we're going to look at, okay, how would the system deform if we made it statically determinate? Okay, I could make it statically determinate by doing the following, and this step is really important. From the given system, we need to make a statically determinate system. From the given system, we are not allowed to take any random statically determinate system we know. Only from this one, we need to remove one force or maybe one moment or put a range somewhere. Anyway, remove either internal forces or external reaction forces so that that system becomes statically determinate. We know that this system is actually indeterminate to the degree of 1, so we need to remove either one internal force or one external reaction force. One possibility would be to keep this cantilever beam. That means I remove the roller support here on the right. Another possibility would be actually to remove the moment on the left clamp support. So I get a pin support there, and I still got my roller support on the right. Those are actually the only two possibilities that we can get out of the system, the only two statically determinate possibilities out of the system. And what do we do with those? We don't need two of them, we only need one. I was just showing the possibilities here. On one of those systems, we put the external load, and that's what we're gonna call zero system. Why do we call it zero system? It's basically because the force that we removed here, what did we remove? The BV. We can, let's say it's an unknown first that we call x1. That's just like convention stuff. We can still call it BV. But x1 here in that system is first 0. So first we're not considering it. We're just considering that the system is statically determinate. So that support doesn't exist. The value of that force, it's supposed to be 0 first. That's why we call it zero system actually. Okay, and then from that system we're going to compute the displacement. How does this system deform, or better said, how would this system deform if we actually didn't have this vertical force here, this roller support, the BV support, the BV force, the B support? Then we do the following. We move to a so-called one system or unit system, call it as you wish. It's actually the same system, so don't get fooled by the name. The 0 or the 1 just got to something to do with the fact that the x1 is either 0 or 1. So on the same stationary system, we put now the x1 force with a value of 1. This is just a unit value. At the end of all of this, we're going to get the real value of x1. Here we're just saying, okay, supposing that x1 would have a value of 1, how would the moments look like? And then when we got the real value of x1, we know that we can just multiply that value times everything we had here, because we're still in the linear elastic theory, by the way. We're in the linear elastic theory here. Yep. And we also want to know how this system will deform, and it will deform like this. I'm just explaining everything that's happening here. That's why I draw deformations and stuff. But in the real step of the first method, you actually don't need to go that far as drawing the deformations. We're gonna compute them. Some might actually compute them without exactly knowing what they are. But here, I want you guys to know exactly what's happening. And this deformation, we gotta call it delta or alpha, depends on the what convention, whatever, call it as you want. If you want to call it kappa, whatever. Delta 1 0. Okay, the first number here means it's actually telling you which force is concerned here, which reaction or internal force was removed. What did we remove here? We removed that support. So, and the support has, that support was like a force. So when it comes to this delta is a deformation. It's gonna be an actual deformation. I mean, a translation, if you want, if I should call it like that. Because I could have removed a moment, for example, like in this case, and the delta will actually be a rotation at that moment. That's why I'm talking about deformation rotation. So it's actually a vertical displacement, or it could also be an horizontal one. In this case, the vertical displacement at this position occurring because of, okay, the second number here, or the second digit, is gonna tell you what is the load. 0 is like in the 0 system where our x1 is actually 0 and the only load that's applied is the external load. So let's say 0 is external load, but actually 0 is just say that the x1 is 0. So the only load is the external load. Okay, so which deformation is occurring at this position, the position of our external, of our extra force, like the x1 force, because of the external load in the direction of x1. So this delta 1 0 can only have positive values if the displacement is actually going in the direction of x1. But those are details you don't really need to know for now. You just need to do the calculation right. But those details come in handy when you actually want to check if your values are correct, if they're plausible. Yeah. And now what do we have here? For such a value, for example, this one, this value should be negative. I can say that already. Because we know that the deflection is actually going to go downwards. That is what we know already, but you don't need to know it beforehand for the calculation. You should get the right value. But by knowing that, we can actually check our sign, for example. We know that the displacement should be downward, and the positive displacement for delta 1 0 is defined upward. So the value we get here for delta 1 0 should be negative. If it's not negative, we got something wrong. And for this one, in the unit system, we put the force x1. We also need to compute how the system is going to deform, and this deformation here, as you see, should be upward, like logic, we can see it, but we don't need to know it. We can just compute it correctly. So it should be upward, and the positive displacement for it is also defined upward. So delta 1 1 should be positive. By the way, all the displacement delta 1 1 2 2 or 3 3, they should, when those two digits are the same, should always be positive. Always. And I just showed why. Like when we have the delta 1 1 here, is defined positively in the same direction as x1. Okay, and that's exactly in that direction that the displacement is going to occur. I mean, if x1 is like acting upward, like the displacement at this position is also going to act, it's also going to be upward, directed upward. And for that, the value is then going to be positive. So back to the digits, delta 1 1 is the displacement at the position 1, a displacement here because we have a force. If it were a moment, it would be a rotation. Displacement position 1 caused by the not external force, caused by the force 1. Okay, the second digit is like the force. Which force is causing that displacement? The first digit is where is the displacement. So if we had different internal forces here that we had removed, like an x1 force and an x2 force, we could also have something like delta q1, and that would be the displacement, for example, or rotation. It depends on the q, what the q is it a force or a moment? Delta q1 would be the displacement at position 2 caused by the force 1. The force 1 at position 1. So the first number here is the position. Where is the displacement occurring? So I just write where and what kind of displacement is it? I mean, is it a displacement or a rotation? I just write where and what. And the second one, 0 is like the load. Which load? Okay. Oops. 0 is for external load, 1 is for the unit load x1, 2 is for the unit load x2, 3 is for the unit load x3, blah, blah. So that's it. And now comes the compatibility. What we say is that because of this system without our roller support, what not really our system is, because our real system got the roller support, because of this system here, the external load is causing a displacement downwards at this position. Now we know that we actually got our roller support. We don't know exactly how big that force is, but we just use a unit force first just to simulate like what are going to be the effect. And when we're going to find out how big exactly is this force, we can know that those effects are just what we found for the unit force times the actual value. So with the unit force, we got a displacement that's actually going upward. But now in reality, when we got our system, so with both of them, with both the external load and the force of that removed support acting on the system, we should have a displacement at this position that's 0. It's a hollow support. It cannot go upward, neither downward. I mean, can go neither upward nor downward. So the actual displacement that happens in such a system is something like this. But you also don't need to know exactly how the displacement looks like. You just need to know that, come on, it's a hollow support. Like, it cannot go upward or downward in this position. It can just move here to the side, but cannot go upward or downward. So the value of delta 1 here, delta 1 that is the displacement that's going to occur in the positive x direction caused by the x force of 1 times x1, so that we got the actual displacement that occurs. Delta 1 alone is the value if the force is equal to 1, like 1 Newton, for example. But that force is not equal to 1, it's equal to x Newton. So we just multiply the values of the displacement times x, because we're still in the linear elastic area of the stress diagram. So we can just multiply like forces. The forces we have, I mean, the forces and the strains are linearly dependent, basically. So that's the displacement that's going to happen here. Upward should be equal to or plus the displacement delta 1 0, the displacement in the direction of x1 caused by the external load should be 0. I don't need to multiply by anything here because the external load is already what it is. It's an actual load, Q. Okay, it's not a unit load or something. So this should be 0. That's what we call compatibility. So basically here we're saying that this node here can neither go upward nor downward. Okay, it should be 0. That's what we're saying here. And with that we can find x1. x1 is then minus delta 1 0 divided by delta 1 1. We got that value. If we had more unknowns x1 and x2, we will have here two equations of that kind. We'll have something here with delta 1 1 times x1 plus delta 1 2 times x2 equal or plus delta plus delta 1 0 equals 0, and then something like delta 2 1 times x1 plus delta 2 2 times x2 plus delta 2 0 equals 0. And so like different equations, and we need to solve them. If we got two unknowns x1 and x2, we're gonna have two equations, so there's nothing to worry about the number of equations anymore. We should get them. We should have the right number. I'm slowly moving towards an end here. That was like how we proceed to get the x1, and the x1 first was our unknown, and when we got our unknown, well, we can do whatever we want. What I didn't say exactly is that in this zero system, we're gonna compute everything we want. From this system, we can compute the normal forces, the shear forces, the bending moment. Okay, we don't have to compute the displacement. We're gonna calculate them in a certain way. Like I'm gonna show you how we get this value, this delta 1 0. We're gonna do a specific coupling of the moment distribution in the one system and the moment distribution in the zero system, 1 0. To get this value, we couple system 1 and system 0. To get the delta 1 1 value, we couple system 1 with itself. That's how we get them. Why exactly? I'm not saying here. Go back to the video or the German video or whatever. I mean, you don't really need to know it for now. Just need to be able to do it correctly. And yeah, let's finally solve that exercise. It would be nice if we could do it in 9 minutes, so it's gonna be a 1 hour long video. Let's do it fast. So this is what am I drawing there? Sorry. Here's the system we got. The null system. I didn't do anything about this variation, but it's basically the same. With the external load, we can put the external load on it. Okay, you know what? We're gonna use this variation then. I explained already what happened here. Let's use that variation then to solve our exercise. So